Hello guys, let us discuss something about the mica group today. We all know mica is a very important mineral, and time now and again we have seen how mica looks like. It belongs to the sheet silicates, which is also known as the phyllosilicates. Now, the mica minerals normally they are not one mineral, rather they have a range of composition. So the mica minerals as a whole, they show considerable variation in their chemical and physical properties. But one thing is common in that they have a platy morphology. Platy morphology. I hope you understand. Platy means flat morphology. And the second thing is they have a perfect basal cleavage. Perfect basal cleavage. Now, this perfect basal cleavage and platy morphology, they both are the consequence of their layered or this sheet-like structure, which we also call as the phyllosilicates. Okay, so if we have a look at the general components of it, so it is phyllosilicate, that is the sheet silicates. Phylon stands for leaf. So a sheet silicate is formed when SiO4 tetrahedra is linked by three of their corners and extend indefinitely in two-dimension network or a sheet. So you can see here that each of these tetrahedra, all the three corners, they are linked up and they extend in all the directions, to in a two-dimension network or sheet. So the tetrahedra shares three of its corner oxygens. You can see here that the three of the corner oxygens are shared, and therefore the basic structure unit becomes Si2O5. It is this unit which gets repeated. So the most common examples of phyllosilicates are mica, clay mineral, chlorite, talc, etc. And the Si2O ratio is 2:5. Okay. Now, as I just said that the uh, mica, it has platy morphology. So you can see here in this picture these plates of muscovite. It's very clearly seen here how they are showing this platy morphology. They have a perfect basal cleavage. When I say basal cleavage, remember that this cleavage plane is going to intersect the c-axis. Okay, they have a layered atomic structure commonly found in igneous and metamorphic rocks. And as I had told previously, that mica group is not just, it doesn't have a single composition, but it has a range of compositions, and therefore mica group comprises of 37 phyllosilicate minerals. Interestingly, all of them crystallize in the monoclinic system. Okay, so you should remember this, that whatsoever is the composition of a mica mineral, three things will be common: platy morphology, perfect basal cleavage, and crystallization in the monoclinic system. So when we look at the structure of mica, the basic structural feature of mica is a composite sheet in which a layer of octahedrali coordinated Y cations is sandwiched between two identical layers of linked SiAl4 SiAlO4 tetrahedra. So normally it is uh, when we talk about the structure, then it is a composite sheet in which a layer of octahedrali coordinated, we'll just see how it becomes octahedral. Octahedrali coordinated Y cation, it is sandwiched between identical layers of SiAlO4 tetrahedral. And we'll see how this structure goes on. So have a look at these two diagrams. as I have told you previously, that these are the linked tetrahedra, the corners of tetrahedra, which are extending in sheet-like network. So on the left, you are seeing the linkage of the tetrahedra uh, with the tetrahedra pointing up. Here in this diagram, you can see silicon and oxygen, silicon and aluminum with oxygen above it, and these white ones, they are the basal oxygens. So this one is in, if you look it from the top, you will get this view. And on the right hand side, it is the mica structure plan of tetrahedral layer, the same thing. But here, this layer is pointing downwards. Okay, so if we simply overlap these two layers, you will get the repeating units. So it's very simple to draw it. Just make a hexagon first. With the corners of the hexagon, they will be housing the silicon or aluminum along with the oxygens, and in the center of each, in the mid part of each of the arms, just draw a basal oxygen and just keep on linking it up. So this diagram is very easy to draw. Simply draw a hexagon like this. Here, silicon and oxygen, 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 and here. So we get 6 ones, and then simply draw the basal oxygens here. So you will get these repeating units. And as you keep on repeating these units, you will get a tetrahedral layer. Now, once these two tetrahedral layers are linked up together, you will find there is an octahedral layer in between these two units. We'll just see. So if we overlap those two layers now, then the black one here is the bottom SiAl2O5 layer, while the red one is the upper layer. So what has happened? Both these layers, they are now superimposed. And this superimposition of these two layers, it causes the kind of, you know, say for example, if I draw these two layers now, then it will be like this. So we have one of these, and simply now reverse these layers this way. So you can see here that, sorry, we have these layers being superimposed over each other. And in between these two layers here, we will get the octahedral coordination. So this is a tetrahedral layer, this is a tetrahedral layer, and in between we get the octahedral coordinations. Since now in between these two layers we are getting ample space, there you will get different types of ions sitting in it. So in this diagram you can see the, the uh, larger circles, even with the one that is solid or even broken lines, they represent the X ion, which is represented by either potassium, sodium, or calcium. And the purple ions here, they are octahedrali coordinated cations, mainly magnesium, aluminum, or iron. And these green ones, they are the additional hydroxyl ion. We'll see later how hydroxyl ions, they get incorporated in this. So if you see here carefully, these two sheets of tetrahedra, the bottom layer and the upper layer. So these two sheets of tetrahedra, the one pointing upward and the one pointing downward, are superimposed. These two layers, they are superimposed. And once they are superimposed, they are linked by a plane of cations. Linked by a plane of cations. Other than that, additional hydroxyl ions are also placed in together with the apical oxygens. So this is the apical oxygen. This is the apical oxygen. Here, the additional hydroxyl ions, together with the apical oxygens of the inward pointing tetrahedra, they complete the octahedral coordination. We'll see how this octahedron forms along with the additional hydroxyl ions and the apical oxygen. So if you see here this diagram, here what has happened? You can see that these two layers, the upward and the downward pointing tetrahedral layers. So this I am writing TD for tetrahedral layers, TD. They are now pointing towards each other, and the inward pointing part, see how these two layers are linked up by these cations. And these cations, if you see over here, then you will find the different cations which are placed, which may be placed in. Moving further to a much beautiful diagram, see this. Here you can see how a tetrahedral layer, then an octahedral layer, and again a tetrahedral layer. So here now I'll tell you what is the number of different ions per unit cell. And this unit layer, tetrahedral, octahedral, and again tetrahedral, this is approximately 10 angstrom in size. So these two blue ones, they both, you have the two potassium ions. Other than that, you have 1, 2, 3, 4, 5, and 6. So this is 6 oxygens. Okay. Then the black colored dots over here, they are silicon, while the red one is aluminum. So you get 3 silicon, 1 aluminum. Okay. Now coming to the next. So here now you can see the coordination. You have these the open dots, these ones, they are oxygens, and the green one here is hydroxyl. So you have in the next layer 4 oxygen plus 2 OH. Okay. Then in the now this octahedral layer, if you see here carefully, you will find an octahedron here. And in the space created by these octahedrons, you may have the aluminum. So you can have 4 aluminum sitting in over here in the octahedral layer. After that, again the repeating unit, which gives you 4 oxygen plus 2 hydroxyl ions. Then you have the 3 silicon plus 1 aluminum ion. So this is how these are the different number of ions per unit cell. 2 potassium, 6 oxygen, 3 silicon plus 1 aluminum, 4 oxygen plus 2 hydroxyl ion, then 4 aluminum, then again 4 oxygen plus 2 hydroxyl ion. So as I had previously mentioned, that the additional hydroxyl ions together with the apical oxygens of inward pointing tetrahedra, inward pointing, see all these tetrahedra which are inward pointing, there they complete the octahedral coordination, and in that octahedral coordination you have these cations sandwiched between them. Okay. Now why is it that the additional hydroxyl ion gets into it? So the reason is this, which you can see here in this one repeating unit. You can see how that space is created. So most phyllosilicates, they contain hydroxyl ion. Uh, the reason being that the OH is located at the center of the six membered rings. Okay, that six membered rings, the OH is located in the center of this six membered ring. So the composition of that group now becomes Si2O5 OH minus 3. So when other cations are bonded to the SiO4 sheets, they share the apical oxygens and the OH ions which bond to each other, which bond to the other cations in octahedral coordination. So when you say octahedral coordination, they will be surrounded by six of such ions. So it is the apical oxygens and the hydroxyl ion which make up together the six, and therefore you will get the octahedral layers. Now, once this octahedral layers they form, then they take the structure of either brucite, okay, these octahedral layers take the brucite structure. When I say brucite, I am sure you all must be knowing MgOH3. And this brucite layer will be taken up when the cations are Mg2 plus or Fe2 plus. But if the cations will be Al3 plus, then it will be the gibbsite layer. It will be the gibbsite layer where it will become AlOH3. Sorry, this will be MgOH2, not 3. Okay. So this is how it changes the structure of the octahedral layers, provided the ions are there. So if the structure is a brucite structure, all the octahedral sites are occupied and all the anions are OH minus. This is an important point which you should remember while giving the structure of mica, that if the octahedral layer is brucite, then here all the octahedral sites are occupied. None will be left blank. Okay, and the uh, anions, all the anions would be OH minus. While in the gibbsite layer, every third cation site is vacant. It is unoccupied. In the gibbsite layer, every third site is vacant, is unoccupied. And again, all the anions are OH minus. So this is the common thing which is found in the structure of mica. So remember this, what you are seeing over here, this is the octahedral layer. And in this octahedral layer, it will take the structure of brucite if the cations here are Mg2 plus or Fe2 plus, and it will take gibbsite if it is Al3 plus. Okay, all right. Now, when we come to the chemistry of mica group, the general formula is X2 Y4 to 6. So we are now talking about the two cations X and Y, and Z8O20OHF4. So X here could be potassium, sodium, or calcium. Less commonly barium, rubidium, or cesium. Y will be aluminum, magnesium, or iron, or less commonly manganese, chromium, titanium, lithium. And Z will be silicon or aluminum, but sometimes it may also include ferric or titanium. So structurally, micas can be classified as dioctahedral, where the Y cations, they are 4 in number. You know that the Y cations where they are sitting. So Y cations, if they are 4 in number, it will be dioctahedral. If it is 6 in number, it will be trioctahedral. Okay, so if the X ion is potassium or sodium, mica is called as a common mica. While if it is calcium, it is classed as brittle mica. So these questions could be asked in your GSI prelims examination, wherein you can talk about the uh, ions which make them common mica or brittle mica. So the dioctahedral mica, the best and most common example is Muscovite, then paragonite, okay, and brittle mica, margarite. Again, you get three names for the prelim examination multiple choice questions, When if it is asked which of the following is not a dioctahedral mica, and you get these three names, Muscovite, Paragonite, and Margarite, then the fourth one, which is not there, will be the correct answer. Similarly, when we talk about the trioctahedral mica, they are the common micas: biotite, lepidolite, phlogopite, zinwaldite. These are the common micas. The brittle mica, clintonite. Okay, so I'm pretty sure you are hearing these names for the first time if you haven't gone through the books like Dear Hovi Zusman. So, for doing the detailed study of the structure of several minerals, you should read the book of mineralogy by Dear Hovi and Zusman. Now, these common trioctahedral micas are biotite, lepidolite, phlogopite, zinwaldite, and clintonite is a brittle mica. These are all trioctahedral mica. So as it was suggested that brittle micas are the one which have calcium in the X site. Okay, so this is how you should remember that. Then you have very rare interlayer deficient micas, which are extremely fine grained micas. They show more variation in iron and water content, and they are termed as clay micas. Best examples: elite, fengite, sericite. All these are very fine-grained clay mica, and both dioctahedral and trioctahedral, they both are found in the clay mica. So interlayer deficient mica, you cannot say that it is only dioctahedral or trioctahedral. They could be both of them. Okay. Now let us have a look at the common micas. The most common mica that you have come across, it is muscovite. Muscovite. So what is muscovite? One of the most common micas and occurs in a wide variety of geological environments. Uh, Talking about its properties, then it possesses electrical and thermal insulation. Then it shows perfect lamellar or basal cleavage. It has transparency in it. It is transparent because it has low iron content. Muscovite has low iron content and it occurs in books, large blocks. So, books of mica, they are normally muscovite, and as I have already mentioned, it is a dioctahedral mica. Okay, moving ahead, the there could be isomorphous replacements which occur in muscovite. The isomorphous replacements in the muscovite could be isomorphous, sorry for the handwriting in this, isomorphous replacements which occur in muscovite. If potassium is to be replaced, it can be replaced by sodium, rubidium, cesium, calcium, and barium. If you are replacing the octahedral aluminum, then here it can be replaced by magnesium, ferrous, ferric, manganese, lithium, chromium, titanium, and vanadium. And if hydroxyl ion is being replaced, it can be replaced by fluoride. Okay. Muscovites, they have often been reported with appreciable Fe2O3 content, but it can vary again. Most muscovites, they contain less than 1% of magnesium oxide. And then um, there could be these muscovites which are fine grained, muscovite. They are sericite, very commonly found uh, mica mineral in the weathering of the rocks. Once they alter to argillaceous rocks, you could find those sericite, and as I have previously mentioned, these are the clay micas. Okay, if we talk about the paragenesis of muscovite, it occurs over a wide range of metamorphic grades. Okay, so when we talk about the Paragenesis. Paragenesis of muscovite. It occurs in a wide variety of metamorphic grades which can exist from green schist to amphibolite facies rocks. Muscovite can occur from green schist to amphibolite facies. The principal metamorphic occurrences of muscovite can be found in rocks like metapelites, then it can be found in metamarls, then it can be found in metagravax, metagravax, then it can be found in uh, metamorphism of impure limestones and of intermediate to acid igneous rocks. In low grade environment, it is formed by recrystallization of clay minerals. And if the grade is above the upper amphibolite facies, it is commonly dissociated to form potash feldspar and aluminum silicate. So sometimes muscovite has also been found in blue schist facies rocks together with glaucophene, lawsonite, and sodium pyroxene. Okay. In acidic igneous rocks, muscovite is less common than biotite. And then it is also very less common in sedimentary rocks. All right. So I hope you would remember in what uh, type of rocks muscovite can be found. Now, another important mineral. Sorry, I'll get another slide to show this to you. Yeah. Another important and commonly found mineral in the mica group is biotite. Biotite. So, muscovite, it was a dioctahedral mica. Biotite is a trioctahedral mica. And it has a range of composition. It is not one mineral. So, a biotite can range from siderophyllite. hmm, The range of compositions in biotite can be siderophyllite. It could be Nite, ANNITE. It could be phlogopite. Okay, so the range of that is why if you'll if you want to be technically correct, then biotite cannot be written as just biotite. It is always biotite phlogopite in association because of its range of compositions. Similarly, like muscovite, biotite occurs in a greater variety of geological environment than any other mica. So, biotite is a more sturdy type of mineral which occurs in metamorphic rocks under a wide range of temperature and pressure conditions. Unlike muscovite, there could be a variety of temperature and pressure conditions for biotite. Normally, biotite is abundant in many contact and regionally metamorphosed. So, contact and regional metamorphism. Contact and regional metamorphism are important for the occurrences of biotite. It is also common in plutonic rocks. The biotite is common in plutonic rocks like granites and granitic pegmatites, granodiorites, tonalites, norites, etc. Biotite is less common in volcanic igneous rocks. Okay, so this becomes the various types of properties and differences between biotite and muscovite. But most importantly, what you need to take away from this lecture is the structure of mica. So to start with, if a question is asked, discuss in detail the structure and paragenesis of mica group of minerals. So first of all, you have to start with this structure. Try making these hexagonal structures with the corners. They will be having the silicon or aluminum with oxygen above and below it respectively. After that, simply superimpose these two layers. Okay. Once you superimpose these tetrahedral layers, in between those two superimposed layers, you will be getting the octahedral layers. And those octahedral layers. So here you can see that how the X ion of the lower and upper tetrahedral layers are shown by the open circles, whether solid or with broken lines. So once you put in the two tetrahedral layers, the space between those two tetrahedral layers will give you the octahedral layer. And this is how these octahedrons are formed. So try to make four tetrahedra on each side, with one tetrahedra showing all four oxygen. Means this tetrahedra, this one, this, but the first tetrahedra, this one is pointing up and then down, again up and then down. After that, simply link up these four oxygens and two hydroxyl, the green colored ones, as I have just shown here. Once you link them up, and then similarly with the lower layer, once you link them up, you will start to get the octahedral layer in which you can house these four aluminum. And after that, once you get this structure, you will simply find this type of an octahedral coordinated structure, which will be either brucite or gibbsite. So try to practice these diagrams, and I personally assure you that if such a question is asked in the GSI mains examination and you simply draw these three or four simple diagrams, these are very easy diagrams, you you will be getting the full marks or maybe the best marks for such questions. If you don't understand anything from this structure part, you can always post in your questions. I hope uh, you are doing good and preparing well for your examinations. All the best.